Welcome to sitza.com. Addition of HBr to alkenes in presence of peroxides. When you add HBr to alkenes or any halogen acid to the alkenes, it follows the Markovnikov addition. That is what we have learned in our previous video. However, in this video we're going to learn about the Antimarkovnikov addition. When you add HBr to an asymmetrical alkene in absence of a peroxide, we know the addition follows the Markovnikov rule, right? And we have learned it in our previous video, how the Markovnikov product will be formed. And according to the Markovnikov addition, when you add a HBr to this asymmetrical alkene, hydrogen is added to the double bonded carbon that has more number of hydrogen. So in that case, the hydrogen will add to this CH2 carbon, right? This carbon, and the bromine will be added to this carbon. However, when you add the HBr, same reagent, in presence of any peroxide like the benzoyl peroxide, or you can say the hydrogen peroxide. So in presence of peroxides, when you add, it follows the anti-Markovnikov. Means now the hydrogen will be added to the double bonded carbon that has less number of hydrogens. So hydrogen will go to this particular carbon, and then the bromine will go to this carbon, the CH2. And you break the double bond over here, right? So what will be the product when you add the HBr in presence of peroxide? The product will be the CH2, this carbon will be added by the bromine here, and the CH here will change into CH2, right? The double bond breaks and we add a hydrogen here, bromine here, and then we have CH2, CH3, correct? So this will be the product here. This is the 1-bromobutane, right? 1-bromobutane. And if you add the same reagent in absence of peroxide, suppose we don't use the peroxide, you add this one and this one here, right? So what will happen? Hydrogen will be added to the carbon which is having more number of hydrogen. So hydrogen will go here in this case, and therefore the product will be, the CH2 will change into now CH3, then a single bond CH, and the bromine will be here, and then you have CH2 and CH3. Now this is 2-bromobutane. This is the Markovnikov addition, correct? Anti-Markovnikov addition, or you can say peroxide effect or the Karash effect, it occurs when you add HBr to an asymmetrical alkene in presence of a peroxide. Now the question is why it follows the anti-Markovnikov. Why not the Markovnikov addition, correct? So why? What is the reason for the anti-Markovnikov addition with the HBr? When you add here HBr in presence of a peroxide, what happens? The peroxides, we know they undergo the homolytic bond fission. Suppose we have this H2O2, correct? So in the H2O2, what happens? There is homolytic bond fission. The two hydroxyl groups are formed, the two free radicals are formed, and it is this OH free radical here, the free radical from the peroxides, right? That will abstract a hydrogen from the HBr, correct? So here in this case, HBr will react with this free radical here, and it will abstract a hydrogen here. So in this particular bond there will be a homolytic bond fission now. So what you will get? You get the H2O plus the Br free radical, correct? Now it is this Br free radical that will attack on a carbon-carbon double bond, correct? So we have here the carbon-carbon double bond, and we have an asymmetrical alkene. We got here a CH2 and the CH3. This is the H here. This is H and H. Now, when the Br free radical attacks, right? When this Br free radical attacks, what happens? It has two options. Either it will go here or here. But when it attacks on this particular carbon, the free radical will be generated here, which is a secondary free radical. That is more stable, correct? Now, if this Br free radical attacks on this carbon, free radical will be generated here, which is a 1 degree, and we know the order of stability of the free radicals. Tertiary is more stable than secondary than primary, right? Tertiary free radical is more stable. So when this Br free radical attacks on this carbon, you get a free radical here, correct? So you get this one CH3, CH2 here, right? CH2 and a Br, right? The bromine will be here, and then this CH with the free radical, and then you have a CH2 and the CH3, and then it will abstract a hydrogen there, and then So it will form the CH2Br here, CH2, single bond CH2, single bond CH3 here. So you get a 1 bromo, this butane. The question is why it happens only with the HBr. So you remember, this is the case only when you add HBr in presence of peroxide. Antimarkovnikov addition or peroxide effect or the crush effect is only observed when you add HBr in presence of any peroxide, right? So it doesn't happen with what, if you add the HCl and a peroxide, correct? In that case, addition is not Antimarkovnikov. If you add the HCl in presence of a peroxide or in absence of a peroxide, addition will always be Markovnikov, right? So with the hydrochloric acid, it will always be Markovnikov addition, right? It won't undergo the Antimarkovnikov addition. Why it is like that? Because when you have a HCl, hydrochloric acid, HCl bond is stronger than the HBr, correct? HCl bond is stronger than HBr. The bond strength is more. We have learned here in this case, in the step number 2 here, if this is the number 1, this is number 2, this is number 3, right? So here what we find, the free radical which is generated from the peroxide, it abstracts the hydrogen from the HBr. Actually, it causes the homolytic bond fission in the HBr, and you get a Br free radical there, right? But in case of HCl, the same free radical cannot cause the homolytic bond fission. It cannot abstract the hydrogen from here. Why? Because the bond strength is more than HBr. HCl bond is stronger than the HBr, so it cannot take it this hydrogen from that, and therefore it won't follow the free radical addition. The free radical mechanism won't be there. So that means if you add a HCl in presence of peroxide or in absence of peroxide, in all the cases, there will be the electrophilic addition reaction, right? It will be it won't be the free radical mechanism, correct? With the HBr, if you add the peroxide, the mechanism is a free radical mechanism here, right? But with the HCl, it's not a free radical mechanism, correct? It will again dissociate into H plus and the Cl minus. So because the free radical will not be able to abstract the hydrogen here. So let's take here an example. If you add here, in this case, if you add HCl, so what will be the product? Again, it's a Markovnikov addition, correct? The hydrogen will be here and the chlorine will be here. So the product will be like this. It will be the CH3 now, and the chlorine is here. And if you add here the HBr, what will be the product? Again, the Markovnikov rule, correct? Hydrogen will be here to this carbon, bromine will go here. So you get a product like this. Now this is the CH3 and the Br here. But if you add here, in this case, if you add a HBr in presence of any peroxide, correct? So what will happen? Antimarkovnikov of addition, right? Hydrogen will go here and the bromine will add to this carbon. So you get a product like this. Now this is the CH2, it will be added by the bromine. Hydrogen will be here, so we don't need to represent in the bond line notation the hydrogen, correct? So this will be the product, which is an Antimarkovnikov addition. Hope you got it. Thanks for watching the video. Bye for now.